you last time.
You have beat me in the past.
You say that, but the past is very recent. You always learn from the past. The past repeats itself.
All right, are we ready?
Yes.
Okay.
Go.
Let's do the go time then. Here we go. I'm gonna close out of this. I'm gonna open up this. I'm gonna pop it over. We're gonna do bang bang. Let me close out of work stuff. Let's go over here.
Kill light too. Kill the light. Or give it.
All right. Is that good? All good? Ready to rock?
Ready to rock. Ready to roll.
All right. So in this chapter, we're going to be covering generics. We have introduced these on multiple occasions. So this is not the first time you've seen this. If I'm coughing today, it's because I planted, I made a lot of gardening stuff, and I have unbagged hundreds of pounds of Carroll, and it's everywhere in me. It's a really nasty rock, anyway. So what we have here is these generics, and what generics are supposed to do is they give us an ability to abstract types. So in short, when we write programs in a functional language that's type safe, we write functionality based on the types. That's what that means, right? And generics give us a way to write code that is type safe, that can be abstracted over multiple types. So this is what we need to have if we're not going to go down the rabbit hole of writing different implementations for everything. So if you use something like Perl, I'll give you a case in point why this is necessary. In Perl, we can do something like this. Oh. Perl E, and then I'll say something like here, let's say 5 plus 5, right? And I'm going to get 10, very simple. And I can also do something like 5 plus, and then in the string, 5 dogs. And I get 10. Right, so Perl has a method here of using plus to add numbers to numbers and numbers to strings. And what it does when you add a number to a string is it looks for a number in the beginning of it. And it says if I have a number in the beginning of it, I'm going to use that. And then I'll just forget the string component because that's all I need. That's not a very intuitive method of handling that functionality, in my opinion. It's not a good example, which is why I used it, of this method of making plus useful in different contexts. So plus is always useful in adding numbers, but in Perl it's useful in adding strings if you understand this behavior. And it can get kind of complex. Well, in Rust, we don't have this type of functionality implemented by default, but you still may want to have plus add numbers to numbers and numbers to strings. So that way you can use plus for both of those, right? And generics give us a method to say this is how it's going to work. I'm going to write something that relies on this functionality, and I want it to be implemented for numbers and for strings, or numbers and strings, and different types, right? So it gives us the ability to write this functionality that we have in languages that are not strongly typed in a type-safe way, and we're going to go through a lot of that. So here's an example, and we're going to see in this chapter, I like this way that they wrote this, because it's going to go through an evolution of a program, and we're going to essentially look at these programs, see how they evolve, and then see how we can use this functionality in a very practical case to reduce the amount of code that we're writing, and to hopefully, reduce the amount of code we have to maintain, because that's really what we're getting at here. So we have this number list, and we say vector, and then we have a list of these numbers inside of it. Now all of these are, of course, of the same type. This requires it, right? The vector macro requires, it's essentially going to construct a vector for you. Vectors typically require everything to have the same type, or to be bound by a trait, which we covered, I think, in the last chapter. And here we have all the same type. If we had a different type in there, that macro would give us an error. So then we're going to create a new thing called largest. The largest is going to start with the number 0, the first element of that vector. And what we're going to do is iterate through the entirety of that vector, and if the number that we're looking at is greater than the largest, we're going to set the largest to that number. Very simple. So this is an implementation that will work on numbers, right? So what if we have two different lists that we want to do? Well, here's what we do. We simply copy and paste code, and that's, the folly of a beginner. You'll see this type of code very frequently when people are learning a language, and that's mostly because they want to get the job done. And this is the quickest way to do it. We derisively call this a copy pasta. When we're working at a big company and we see people do this pattern. But copying and pasting is definitely part of the learning process. So there you go. Now we have one list here, one list up here. We're both printing the largest number. There's just a lot of code redundancy. All of this logic here is the same, but we just simply copy and pasted it. Okay, so now we have, this is essentially our intern that wrote this code, and it's dog shit.
He's been fired.
He's been fired. And now we have our junior level programmer down here. And the junior level guy says, hey, here's an idea, let's put this in a function. And then the function now can take any vector of I32s, and it can run it and find out what's the largest number. So there's our junior code. And to be honest with you, this is usually good enough. Usually good enough. Usually you don't need generics, right? So when you're writing your own code, it is not often that you need to make that code generic over something. In fact, if I was to take a guess, I would say the vast majority of code that you write will not have to be generic. So, you should learn this, but you probably won't be using it as much as, this book is not properly weighed, I'll put it to you like that. There are 10 chapters in this book. If 10% of your code is generic, that sounds to me believable. But, it's not going to be, this is not going to be most of your code. So, what we're seeing here is that we have these I32s, and now this works, right? So now we're going to go to the next chapter, and we're going to see the problem with that. The problem with it is, if we want to do something else, like not just I32s, but characters, well, now we're back to copying and pasting, right? So if I say, okay, I want an I32, I think a better example here would have been something like a float, or like an I64, because that seems more conceivable than a character. But sure, I mean, you can have a character, right? Like if I tell you to arrange the alphabet from A through Z, right? You are going to look at that and say, okay, well, A is less than B, B is less than C, C is less than D, so on and so forth. What's the greatest? Z, right? So you can kind of think of it like that too, right? And that's what they're getting at here. The largest character is going to be the one that is greater than the other, and here's the logic to do it. So it's very simple. You can see here between these two definitions, there are only two things that are different. The type parameter from I32 to character, and, which is on both sides, the argument, and the return value, and the name, from largest car to I32. I will say this, it's not just that you're reducing code, but this is also a really stupid pattern. Anytime you put the type name inside of a function name, you know you should be using generic. So there's your hard rule on that. Don't ever put a type name in a function name, because you shouldn't bother people with that kind of stuff. And here's what we have here, function main, and we say let number list equals, and we put a vector list. And then now I have to know, oh, well, this is I32, so I want to call this one. This is the largest car, I want to call this one. This kind of stuff is a real pain when you expose this to an end user. They don't want to have to think about this, they just want to call largest, and that makes sense, right? So here's what you're doing here. They're showing you that if we just modify this a little bit to largest T, now it works. Right? Now we don't have to know in the function name what it is. We don't have to say largest car. We can just say largest. And in order to make that work, we take a type parameter. So we say largest is parameterized over type T. And for any T, any vector of T's, I will return one element of that vector, T. Now, here's the thing too. This is kind of awkward, in my opinion. Let me explain this to you. This syntax here is confusing. And it's confusing because it's a convention that goes all the way back to like the 1970s, and it is entirely inconsistent with the rest of the language, right? So what we do here for arrays is we say something like this. Okay. For an array, we would say something like,
You make it a little bigger.
we would say something like this, let x equals, right, like that's totally valid Rust syntax. This is a little awkward though, right here, that kind of syntax, right? So just so you can see that that should work, if I write it, oh, well, it's because it needs another size. So it's going to be like this and then 3, because it's in a row. We're going to run. Oh, duh. Let me change this for you. So when we accept an array in Rust, we can tend to use this syntax right here where we put it inside of the brackets. And what I'm doing, this isn't actually really necessary in my opinion. It just, I mean, for all intents and purposes, it's the same. But the idea here that I'm trying to show you is that we use these square brackets for arrays. And that is because it is such a strong convention with programmers that we have just been doing that for so long. Rust, rather than challenging that convention, has accepted it. It is inconsistent because it's syntactic sugar for just one type, an array. What you would typically see is something like this, right? If this was like any other type, you would see it like this. That's what you would expect, right? So what I want you to see is that when we do this down here, and they're showing you it like this, if this is throwing you for a loop or looking needlessly complex, it's just simply because that is a one-off special case that only works for arrays. In arrays, you put them in brackets with the T, but in every other type, we use the angle brackets, right, by convention. Anyway, so what we're doing here is we're taking this type T, and we're saying any array of type T, we're going to return one element of it, right? Now, here's another thing too about types. As you learn more and more about typed programming, and you get more and more comfortable with it, you can very frequently determine what a function does just simply by looking at the types that it takes and it returns. Right? So if I tell you right now, I'm going to take an array of one type, multiple elements, and I'm going to return one of them. Generally speaking, if you look at that, you're going to think it's either average, min, or max, right? Smallest, largest, whatever, something like that, right? And it's going to iterate from the entire array and either look for something or iterate through the entire array and tell you what the result of that operation is. You can kind of get an idea of how that functionality works just by looking at the types. And you will see that more and more. You'll feel it more and more as you learn it. But here what we're doing is we have this function largest, and all we're doing is we're returning one type, and we're taking an array of multiple things, right?
How does it deal with multiple types, though?
What actually happens under the hood is this tells the compiler, I need to handle this function for multiple types, and the compiler is saying, for every type you use this function on, I will generate internally a new function. It's a process in compilation called monomorphization, right? And it means that we're going to be generating a new function to match the incoming and outgoing types that use requires, right? So if you only use one type with this function, it'll generate the same code with or without generics. If you use two different types with the same function, you will actually see your executable generate two different blocks of code. Now, the downside to that is that your program can get slightly bigger, your compilation time will take slightly longer. The upside to that is you'll have native performance for both of those types. So you will not see any performance degradation in either one of those cases. What do I mean by that? Let's go back to the Perl example that we did, right? Okay, if I do the Perl example of something like this, Perl E, and then I did something like, say, 10 plus 10. Okay, this is not maximally fast, right? Because Perl is going to look at that when it gets the plus operator, right? Like if I do something like this here, Perl, let's do it like this. My foo equals 10, my bar equals 20, say, foo plus bar. And then let me do this here. I'm going to tell it to print out what it's doing. No, not MO deparse, MO concise. There we go. Okay. So I mean, this is like where we can kind of count a little bit. Just to show you, like, this is the advantage of Rust and why we say Rust is so fast. You know, number one goal is safety. Number two goal is performance. So what we have here is what Perl is doing, right? So you can see down here when we actually take it and we say this add down here, it has to do all of this work above it, right? All of these are different opcodes that Perl is running internally on a virtual machine. And then when it gets to add, it has to look at both the left and the right to figure out what these are. And only after it figures out what they are and how to run it, can it actually perform the operation, right? So it says essentially, am I operating on a scalar or an array on the left and the right-hand side? If I'm operating on a scalar, does it contain a number or a string? Like, all of that logic is something that Perl has got to be doing in runtime. And that means that just adding something like 10 plus 10 in Perl is a substantially more complex operation than it is in Rust. Because in Perl, you don't get native speed. The whole entire language itself has an overhead, right? The same thing is true with Python. It means that these languages tend to run slower when you're using them because you're paying a performance penalty for the fact that the language isn't compiled. It's doing all this stuff in runtime. Now, when we do something like this with Rust to say, like, how does it get it done? Rust is going to generate two different copies of these functions internally. You won't know them. And it's going to essentially say, in compile time, if you're taking two numbers, call that function over there. If you're taking a number and a string, call this function over here. And then when they get run, all of that resolution is already done. So it just happens natively. You know, there's none of that deciding in runtime. All right. Anyway, so here we're doing it now with a vector of numbers, and then here we do it with a vector of strings, right? Of characters, rather. And that's that. Another thing that I should say here is that this syntax up here, yes, let's take it, let's try this here, let's see this. I am pretty sure that this is going to work like this here. Nope. I need to fix that copy. Oh, because this is the broken one. They want us to run this code. Okay. So, yeah, let's cover this before I go into that other component. So what they're showing you here is that in order to make something generic that determines whether or not there's a larger element, right? In order to be able to find the largest element in an array, you have to fundamentally be able to compare the elements inside the array, right? You've got to be able to say that given any two elements inside of this array, which one is greater than, less than, or equal to, right? Can I compare them? Are they equal to each other? Is the left greater than the right, or the right greater than the left, right? So that functionality in Rust is done through a trait. There's a trait that will tell you that these two things can be compared. That functionality is implemented for you. And that trait is right down here. When you run this code without the trait bound, it actually tells you. It's stdcmp partial order. Partial order is the name of that trait. Partial order means that it's returning a maybe with equal, greater than, or less than. So what does that mean? That means that if I give you two things that cannot be compared, partial ordered will return null, rather none. It'll say I can't compare these two things. And that's true. Like let's say that I want to implement partial order on my own type, and I'm implementing a type for people, right? And then I'm saying I'm implementing partial order on people. Well, if I want to say, okay, if you're getting a car and a person, and I say which one is greater, you may want to return I can't be compared against cars, right? You represent that with none. And that's what partial order does, right? So let's come down here and I'll show you how we can see more information on it. We can always go up here to like the Rust search extension and search for that type. And here's where it is, partial order. And you can see here that partial order is going to return an option of ordering, right? And this ordering is an enumeration that returns less, equal, or greater. So partial order implements these four functions, right? And this one, partial CNP, and all of them are going to return an option of ordering, right? Less than, greater, or equal, or none, right? Because it's an option. So we have this type here, largest, and then this function largest, and what we're essentially saying is, in order for largest to do its work, in order for largest to figure out what is the largest element in that array, or that vector, it has to have an implementation of partial order. And this is how we say that we can only call largest on an input that implements this trait over that type. And this is what makes that whole thing work. So when we create this generic function, largest, it is leaning on this functionality from this trait. And that's why it has that boundary there. So let's take a look at this. Let's just show you here how we fix it. If we come over here and we run this code that they gave us, we have this error. In order to make it work, I'm just going to add this here. Up at the top. And now you'll see it compile. The largest number is 100. The largest character is Y. Okay. So we have to have stdcmp partial order. I'm going to say one more different way. Because of this line right here. That's what that error was about. Because in order to say whether or not item is greater than largest, it requires this trait to be implemented. So we have to say to the compiler that we can only accept types that implement that trait. Otherwise, we can't run this piece right here. Likewise, let's go back to the addition thing, right? If you were going to do addition, right, you wanted to make it to where you were accepting two types that could be added rather than compared. There's another trait for that. STD, I forget what it is. Add and STD ops, there you go. So there's a trait called STD ops add, and it says that two things can be added together, right? Or you can add something to itself, right? So those traits are there for that, a different piece of functionality, but it's roughly the same idea. If you want to use add to an input, and you don't know what type it is, you're going to have to say that the type that you get implements add. All right. So now we have this thing called derivable, and we definitely 100% covered this in an earlier class. Does anyone remember what derive is and why I said it's magical? Okay. So it's not a problem. These are methods in which we can implement functionality we don't have to write ourselves. So when we get down to like what two things can like be compared and added together, be checked for equality, implement display, all of these types of like very basic pieces of functionality, we don't want to write that code ourselves. So this piece of functionality, derive, takes a trait name and it will implement that for your type if it can. Right? So, for instance, derive can give you a default implementation of debug. Right? I told you earlier that if you want to print something out to the terminal, you have to implement debug for it or display. Display presents to you a nice user-facing text message that tells you something about the type. Generally speaking, you implement display. because you're telling your user something about whatever that type represents. Debug is for debugging things, right? So you don't want to have to write the code to say how you're going to dump this type to text. You just want to see JSON or YAML or something like that whenever you look at that type, right? So if I'm selecting a row from a database and I want to debug that row, what I want to see is all the columns with the column name on the left and then the value on the right. You know? But what I don't want to do is say for every row that I get, here's how I'm going to release the debugging information. I'm going to iterate through that row, taking all the columns on the left and putting out all the values on the right. You don't want to write all of that code every time. Derive gives you the ability to automatically generate it in compile time for those traits. So here what they're doing is, they're saying we have an enum, which is called E, right? This is not a type. This is actually the name of the enum, is E. E implements top and bottom, and it's going to derive partial ek, that's how we pronounce this, partial ek, and partial order, right? So what is partial ek? Partial ek means you can derive for equality. So I can compare now two E's to see whether or not they're equal, right? There is no rule that says that an enum, like this enum, if I didn't have this, I would not know whether or not one top is the same as another top, right? You wouldn't have that information. How would you represent, if the top, the roof, for instance, if I say enum, roof, and then floor, for instance, how would I know that one roof is the same as another roof? Are all roofs the same if I compare them? Right? So if you use derive and you say I want to derive partial ek, it's going to make the assumption that every single variant of that type is the same, right? That they can be compared. And with partial OR, it's going to make the assumption that the one on the top is lower than the one on the bottom. Right?
Makes sense.
So that's what these derive statements do. Now, generally speaking, I don't implement partial OR with derive. I do implement ek and partial ek all the time with derive. But if you implement this, here's how you would implement partial OR. So we just saw an example where we were doing largest, and largest relies on this functionality with partial OR. Right? So we just told largest, right, when we were doing it. Let me show you this. We're going to go back over here and look at this when we do, well, we're past this one. It's, there we go, here we go. Yes. Oh, actually, we're on a whole different thing here. I am showing you the documentation for partial OR. Okay, good. So here, this is actually really useful. So here, we had this, we just did function largest, and I showed you here how we do this stdcmp partial OR, right? This says that every type that I'm getting from largest, it has to implement stdcmp partial OR in order for this function to work. In this documentation page that we just so happen to be looking at, they're showing me how to implement that, which is very handy, right? We're saying implement partial OR for person. So imagine this was our type, and we wanted to be able to provide it to largest. You want to know which person is the largest person. There's what your person looks like. How would you make largest work on that person? You have to implement partial OR and nothing else, right? Because if you implement partial OR, what's going to happen is your implementation over here that just says it needs to implement partial OR will be satisfied. And what does it look like to implement partial OR? Well, you implement this. You say IMPL partial OR for person. That means I'm going to implement the partial OR trait for my person. And that trait, right, requires me to implement partial CMP and nothing else. Partial CMP says I'm going to take myself and what I'm being compared against, and I'm going to return an option of ordering. And what I'm going to do here is call self CMP to other, right? So I have an internal method called compare, and I'm going to just look at the self CMP to other. So here's what it looks like to implement partial OR for a custom type that we would then be able to use with our largest. This is actually a really good way to expand on the book.
And then the self-CMP method could be, you could compare the name, length, you can compare the, whatever you determine, or height, I guess is probably the one you want to do here, but you can do whatever you want to determine how you want to order people.
Okay, so here's how it actually works, right? This example is, again, slightly more complex than I think it needs to be. Because we have different variants for order, right? We have partial order and we have order,
Okay.
right? And the thing here is that partial order is relying on self.cmp. And your next question should be, well, what implements self.cmp? That's implemented right here with implementation of order per person.
Okay.
So partial order can say, I can't be compared. Why is that useful? Let's say you're comparing floats, right? One of the values for a float is not a number. Has anyone heard of that? That's one of the reasons why floats are more complex, right? So if you take a float, you have a lot of things to do with it. Let's open it up node. And if I say something like 1.0, right, divided by infinity, I get 0. If I say infinity times infinity, you get infinity. There is a way here, though, to say like, let's try this, 1.0 times, maybe even a, there you go. That's going to return NaN, right? NaN is actually a float. So this NaN component is very complex. This is why floating point numbers are entirely more complex than regular non-floating point numbers, because a floating point number can represent something that is not a floating point number internally. So what do you do when you compare floating point numbers and you have not a number in it? If you say F64, one of the potential values for F64 is not a number. So if you're going to compare 1.0 to not a number, what should you return? Like this, right? 1.0 greater than not a number. What is that going to return?
False.
False, because JavaScript is stupid. It doesn't do floats right? What you ideally want that to say is can't be compared. Exactly. Because you can't compare 1.0 to not a number, right? So Rust gives you the ability to write code that does that kind of thing. And that's what this is about.
So in your own implementation of partial order, do you have to call self.compare, or you could implement your own comparison function here and it would just call that instead?
You can implement your own comparison function, we'll just call that instead. But if you can compare any person to any other person, right? If you can make that comparison, then you can implement order, not partial order.
Okay. And
So here's how it works, right? Let me think about this. Okay, yeah. When you're comparing two things, right? There is a subset of functionality, right, that you can have called ordering. And the thing about it is, it only models a small part of the potential domain. So if I say, can I compare two tables? The answer is probably yes. Two chairs? The answer is probably yes. Right? For these types of things, you can just implement ORD, right? Because they can all be compared, and ORD is stricter. Because ORD doesn't return an option of ordering, it just returns the ordering, right? So it's stricter. It returns something more useful than partial ORD. Partial ORD is a superset. It's handling things that may not be able to be compared, right?
gotcha.
So we wrote a function, largest, and it is not requiring us to be able to compare everything internally. They can all return maybe, or whatever, rather none. And what are they going to do in that case if everything returns none? Anyway, the point here is that the ORD is going to handle more cases because it can represent things that can't be compared. So we're writing rather partial ORD can represent more cases because it can represent things that can't be compared. So in here we're writing the implementation for ORD, and then we're simply saying partial ORD is going to lean on that.
Okay.
Now I thought this was confusing when I first learned it, but there is also a partial EC, right? And partial EC returns things that, hold on, wait, because I'm remembering I was confused, I don't remember why. Let me actually take this back one notch. let me open up a terminal and let's do the Stack Overflow. And let me hit this up. And I'm going to show you where I had problems here. Newest. Yeah, here. Why does partial F return a bool when partial or is more nuanced and returns an optional order? Yeah, let me see something here. Let's see here. RS X. All right, let's hit this up here. Okay, so because I forgot this, I have to look this up here. There is a trait called partial EC, and there is a trait called EC, STCMP EC, and EC is going to return. What was the difference between these two? EQ and non-EQ. EQ implies partial EQ and has no extra method. Okay, yeah, let's ignore that entirely. Okay, rather than going down that rabbit hole. Yeah. In this example, they're also implementing partial EC. And all that they're doing here is saying that for EQ, there is self and other, and they're just simply saying whether or not they're equal based on height.
Gotcha.
Right? And by the way, you can derive, like they're deriving here, EQ, which is what was storing you for a loop, and then they're implementing partial EC on it. The reason why they're doing that is because you can compare any two people for exact equality using EC, and then you can declare any two people just based on equality with partial EC using just their height.
Oh, that makes sense. Okay.
Anyway, it's goofy, but whatever.
That's useful for comparing structs, I guess.
So instruct definitions, there's an ability here to take parameters for this too. So we've used structs before. In fact, I think every lesson has used structs in some capacity. They're very fundamental. But here what we're looking at is we can create a struct that can accept different types. So rather than creating a struct, for instance, like of a point that has floats and a point that has F32s and F64s and whatever, we can create a point struct over type T, right? Now, X and Y can be of any type. Now notice I said X and Y can be of any type, right? Any one type. They can't be of two different types here, because we have one type variable at the top, so it's saying X and Y must be of the same type. Alternatively, you could say point T, T1, T2, and then say here T1, T2. You could create a point of any two types. All right. And here's what they're doing. They're showing you that it won't work because these are different types, right? This is an integer. This is a float. This is one type variable, so you can't set it to two different types. And here's the error that you're getting. Because this is an integer, this one must also be an integer. You expected an integer, but you found a floating point number.
That's specific, huh?
It's pretty specific. It's good. The struct point, now here's what we're showing. We're showing you it taking two different types. We have the X, which takes a T, and the Y, which is a type U. And now we can give it two different types, and the compiler doesn't complain. We covered option earlier, and now we've seen types in struct definitions. This is where I think it goes a little bit quicker. Now we have types in enum definitions too. So what does that look like? We've already seen it with option. We covered option and result extensively in the last class. Here's an option of type T, and some takes a T and none does not, right? And I even showed you these two things and compared them next to each other. Result takes a T and an E, and OK is of type T, error is of type E. Nothing represents both types. You either create an OK or a result. OK can be of type T, error can be of type E. And in method definitions, we can also accept these generics, and they all work the same. This is consistent across the whole language. So if we get it in one place, we should get it in all these places. Struct point of type T, and here we go, two of them that are the same. What does it look like to implement functionality on this? It looks like this, right? This is what we're saying. We're saying we want a struct that has X and Y of the same type, and then I want to implement for anything of that type a function called X, and X is simply going to return that type, right? And what is it going to return of that type? Self.x. Does that make sense? So create the type, and then return X for it. Point, we're implementing point now for just F32. So where we did this up here, we would say this is an abstract, a generic implementation, right, over point of type T. We would say this down here is an implementation for just point of F32, right? So if we implement distance from origin for just point of F32, what happens if you call it on something that's not an F32?
It won't go to the implementation. Or not, distance from origin won't go to that.
Right, so what are you going to see? Compiler error, right? Yeah, you're going to get a compiler error. It's going to say you didn't implement this on this type. So it may tell you something like you implemented it on this type. Maybe you mean to use this type, or it may also just give you an error message that says implement this, for a point of type F64 or whatever. So here's a struct of point with a point struct with an x1, y1, and now we can accept two different types, and we're simply seeing now what does it look like to implement on that point. Well, here we create an implementation, and it takes two type variables, so this is always reproduced, right? Struct point with two type variables, and implementation is going to require two type variables. So we say, I want to have an implementation with two type variables, and I'm going to be creating it on this, point of x1, y1. So this is how you declare the variable, right? And this is the same way in something like JavaScript, you use let, right? This is a way of declaring not a variable that holds a value, but a variable that holds a type. You declare a variable that holds a type in the brackets of the implementation. And then you can use them later on. So I'm declaring two variables here, and I'm using them like this. Now I say here fn mixup, and I say x2, y2, right? So now notice, where are the x2 and the y2s?
On the function declaration.
Well,
But we're using them for this other point.
that's exactly right. There you go. That's what I'm looking for. There is no x2 and y2 in the code that I've highlighted, right? Well, that jumped around. There is no x2 or y2 in the code that I highlighted, right? And the reason for that is simple, because it's expecting that from the argument. Those type variables aren't for the thing you're implementing the functionality on. Those type variables are for the thing that you're receiving as an argument. So there's two different type variables for the struct, right? Point can have any x of one type, any y of another type. Well, I am creating functionality so abstract, I can take a point with any two type variables, and I can compare it against another point with any other two type variables, right? They don't even have to be this. So I can have x is a string, y is a person. I can be a point, and then my other point can have x of type dog, y of type cat, and then I could still say mix up. And what is it going to return? It's going to return the x from the first one and the y from the other one. Right? Now, in this context, the point doesn't make any sense. It has no real meaning like point anymore. So it's not really useful, but this is just showing you the power of like generics. Okay, performance of code using generics. I've already explained this. Generics are extremely fast, and they get monomorphized, and that should be it right there, monomorphization. And that just means you are generating one copy of code for every use case. And you're going to run at native speed. And that's it. Okay, 10.1 is done, 10.2 and 10.3. 10.2, defining shared behavior, defining a trait. Okay, so far we've seen how to implement functions on traits and on enums, but we have not seen how to define our own trait, right? And this is also something you very frequently do. I think this may be the first time we've defined a trait. So in order to define a trait in Rust, it's very simple. You say pub trait or whatever trait. You don't have to make it public. Your trait name. Then you say what you want your trait to demand, right? So here I am saying my trait, in order to implement my trait, you have to implement a function called summarize. Summarize is going to take a reference to whatever you implement it on, and it's going to return a string. This is what we would say is the trait declaration. You're declaring a trait. I am declaring a trait, named summary, which requires those that implement it to implement a function called summarize, or a method called summarize because it takes self, that is going to take self and return a string. Now, when someone takes your trait declaration and they implement it, you would say they are defining that behavior, right? So you declare the behavior, they define it when they implement it, right? They're going to say how it actually works. Implementing a trait on a type. So now we're going to see how that works. We have public struct news article, and we say here implementation of summary on news article. Summarize is a function that we're requiring to be implemented, right? We said that right here. We require summarize for summary to be implemented. We are implementing summary for news article. So now we're going to have to declare summarize. And this is what it looks like. Function summarize takes a self, returns a string, and then this is how I want the summary to be. That's going to be the string that I'm returning. So we've implemented it now for news article. Here's how we implement it for tweet. Tweet is going to be fn summarize, takes the tweet object, and it returns a string, and I'm going to just print out the username and the content. So now I have a summarize implemented for both news article and tweet. Okay? Now this is useful because now I can create a function that takes either a news article or a tweet, and if all I need to do is call summarize, it doesn't make a difference. Right? So if all I need is a summary of whatever I'm given, I can now make a function that can operate over this type and this type by trait bounding it to summary. I can say for any type that implements summary, right, call summarize internally, because that's the one piece of functionality I can do, and I can get access to it. Access to the result here. Okay, so then here's what we're doing. We're declaring a tweet down here, and they're just showing you that it works. So they're calling tweet.summarize. Now remember, when you, well, let me see when you do this. They're not doing it yet. We'll get to that later, or I'll do background. Public trait summary, they have this summarize, and they're showing you here that you can have a default implementation. So I just told you that we were declaring our trait. We were declaring our trait because it did not have an implementation. Here they're showing you a trait that actually has the implementation to it, right? So this provides us a default implementation too. So this isn't just declaring summary, it's defining a default implementation of summarize. So now anyone who doesn't define summarize will get this, read more. This is kind of nice because you can have like a backup or a fallback, you know? I can say, if you want a summary, you can take the work of writing the summarize feature. If you don't, I'll just print out read more. And here's how that works. Now I have news article available, article.summarize, and it says new article available, read more. Why? Because news article, we didn't implement summary for it. Right? We implemented summary for...
I think we did actually. But
Did we? News article, we did implement summary for that.
I guess it's in this new code example, it's not there.
That must be what you're trying to do. That's also confusing. Yeah. To implement the default blanket implementation, for instance, of news article, we specify an empty IMPL block with IMPL summary for news article. So they're saying in this case, we're not actually writing this. Let me show you. See down here they say IMPL summary for news article, and then they write the implementation inside of it. They're saying down here, in order to get the default implementation to run, they're reducing that to just this. IMPL summary for news article, open and close. They're not writing it. Okay, so now we have a public trait summary, and it has two different things, summarize author and summarize, right? And here's the deal with it. They are defining a default implementation of summarize, and they are requiring an implementation of summarize author. So here, you have to tell me something about your author, summarize your author, but you don't have to write a summary for anything else. It'll define you a default a summary. And then there you go, that's how the summarize author is, just as the username. Traits as parameters, here's the syntax. I don't particularly like it, but a lot of people love the syntax. If you love the syntax, that's cool. I think it's made for new people, so by all means, use it. I find it to be slightly more confusing and more to wrap my head around.
So this is rather than having like the try, or the, I don't know what the brackets are called.
Angle brackets,
Angle
right? Using the angle brackets, right. You can
You
write
would
this.
say ampersand and full summary.
Right.
Okay.
Right, so here, this is
And-
how the new school does it. And this is, the reason why I say new school is because I think that the only reason why I'm not used to this is because I'm old. This is how they write it now. A lot of people write it now. This is how we used to write it, or how this is how we wrote it in Haskell, which is my basis for doing this before this language. If I say here public notify, I could say T that implements summary, and then I would say IMPLT. So this is what I'm used to here. This is what the syntax they've given me down here.
Gotcha.
And the reason why they've done this, right, the reason that sold this over is for an example that we'll come to in a bit, and then I'll explain that a little more. Public function notify, item, IMPL summary. Okay, this is what we just covered. This is just that new syntax. So they're showing you essentially that item can take this, anything that implements summary. We're not specifying the type. There's the trait bound syntax. This is what I'm used to. So they actually wrote it down there specifically. And here's the reason why they implemented this new method. So in this one, we have item 1 and item 2, right? Here's what they're doing. They're saying item 1 implements summary, item 2 implements summary. This is nice because they're not saying that item 1 is the same as item 2. Down here, they're saying that item 1 and item 2 are of the same type. So here, notify has to take two items that are the same. Here, notify can take two different items that are different. Here is how I would write the same code using old people way, right? We would do this, right? FN notify, and then I would say here T1 summary, and then I would say T2 summary, and then I would say item 1, there you go.
Gotcha.
So you can see how this at the top, or what they gave us over here. This one is slightly clearer. So there's your two different styles. These two do the same thing. And I really think that it totally depends. This method here is probably also more efficient if you read types before you think about things. Like I would prefer to just see the types and figure it out what they do, like mentally. That makes it clearer to me without having to read, function names and arguments and parameters and all that kind of stuff.
Yeah.
Now I can just see that type 1 and type 2 implement summary, and that's what notify takes. It takes two different types to implement summary. Let tweet equals tweet, username string from horsebooks, ebooks, content string from something else, print, tweet summarize. Okay, we did this. This is old, this is old. Trait bound syntax, okay. So we talked about how after we implement a type for two different things, we can declare a function that takes any type that implements that, right? Rather, let me rewind. We can implement a trait for two different types. After we implement a trait for two different types, we can declare a function that will operate off of any type that implements that trait. That's what they're showing you here. they're showing you we've already implemented summary on 2 different types. Now I'm going to implement notify, one notify that works on both of those implementations. And what does it do? All notify does is say breaking news, and then it calls item.summarize. And the reason why this works is because summary provides item.summarize, and that's all you know of that type at this point. So the only thing you can get access to when you use a trait bound is what the trait implements, or any super trait of that. So if you have a subtrait, you can implement anything that requires a parent trait. Okay, so here we have public function notify. It takes item 1, which implements summary, and item 2, which implements summary, and didn't we just do this? Oh, okay. We already covered that. I don't know why they're showing it again. I don't know if I scrolled up on accident or something. Okay, here they're showing you that you can, we've already declared, we showed you that we can accept a function that takes any type that has implemented a specific trait, right? But that is almost never enough, right? So where I said you very often won't be using generics, you will very often use these type bounds, right, when you're writing code. Because you can't, if you want to write a function, for instance, that calls display, at the very least, you're going to write a trait bound that makes sure your type implements display. So this is very common, right, this trait bound on display, because you want to get something to a string or something. So this is what I'm used to seeing down here. You would just say trait 1 plus trait 2. That means that T has to implement both of these. And item can implement it like this, right? Item, and then you put them in parentheses. You say implementation summary plus display. Whatever you feel more comfortable with. I actually feel like this is, why is only the first one on MPL summary, not the second too? I don't know, whatever. Clear trait bounds with where clauses. Here's another way to do this. So what happened here is, before this syntax people were cool with it, everyone was writing code like this, and we started to have a lot of different trait bounds where you'd have 1, 2, 3, 4, 5, 6 traits, and it just would look like T would just keep getting carried on. And what they ended up doing was this, which I actually do kind of like this. This is the where syntax, and here they're saying some function takes a type T and a type U, and T is here, right? The argument T is a reference to T, the argument U is of a reference to U, and it returns an I32. Now they're saying T is bounded by display and clone, and U is bounded by clone and debug. So this allows you to move this stuff up here, where we have display and clone, into lower syntax, right? So you can put the boundings down there. You just declare the variables at the top and then the trait bounds below. Returning types that implement traits, you cannot do this, right? And the reason why you can't do this is because 2 different types that have the same implementation may be of different sizes. So the compiler will error if you try to do something like that. Everyone tries to do something like that and it never works. Now you can actually return a dynamic type, which you'll see later on, is the solution to that in chapter 17. Using trait bounds to conditionally implement methods. Here's an example of that. Here what they're saying is, for any type T that implements display and partial org, for a pair of type T, I want to implement compare display. So if I've implemented this and I've implemented this, I can implement this for free. CMP display. If I can compare it and I can already display it, I can implement something that compares it and then prints it out to the screen. And that's the end of this. Okay, last one. Validating references with lifetimes. Does anyone have any questions over anything we covered thus far? Because now we're going to get into lifetime stuff. And you can also see this is a long chapter. All right. It's good because we almost have half the class left. Lifetimes are another kind of generic that we've been using. Lifetimes are the complex ones that nobody likes because they require us to think about things that other languages let us ignore, right? So here's how we want to think about code. We want to think about it like this with just brackets. it gets more complex than this, and we're going to see that in this chapter. This obviously will not work. Why won't it work? Who wants to explain this to me? Give it a shot.
Because R is, okay, so X is being let out of scope, and R is a reference to X, so it can no longer reference something that went out of scope when it was dropped.
That's exactly right. X goes out of scope right here because it's declared in this scope. So R can't hold a reference to it. That's where that goes. The borrow value doesn't live long enough is the Rust way of saying that. You're borrowing the value here, and it doesn't live long enough because the whole type goes away, right? And the way we think about this is, what is responsible for destruction in Rust?
Well, when drop is called the end of like a bracket, basically.
Remarkably good answer. But what's the Rust way of saying that? What calls drop? Whatever owns it.
Okay, yeah.
That's the right way, right? That's the word I'm looking for, is ownership. Ownership determines who cleans it up. The problem here is that 5 is owned by X.
Yeah.
So R can't borrow X because what owns this 5 is X, and it doesn't live long enough. When this goes out of scope, then X, which owns the 5, will call the destruction, the drop, right? That's the reason. And here's where it actually tells you that. Dropped here, less than 1. So let's put it right in the face. Now, we talked about type inferences, and we said in Rust you can kind of think of everything as having a type, but you don't always get bothered with it, right? And I showed you different examples where we don't declare a type, but Rust figures it out and makes the whole program work. And if it can't make it work, it comes to you and says, hey, I can't make this happen. But I showed you this with like underscores, if you guys remember in your other classes. I kept saying type inference is what makes this language doable, right? And it's something that you really have to have, in my opinion, to have a strong type language. Okay, well, it turns out that Rust doesn't just infer types, it infers these things called lifetimes too. So anytime you have a reference in Rust, there is a lifetime associated with it. The difference is you don't have to write it all the time. So very frequently, you have a reference in which the lifetime is implicit, right? That means that it lives entirely in the kernel, in the Rust compiler rather, and you don't get bothered with it. What it's showing you here is how Rust actually sees things. And I would argue this is still probably, no, this is good. This is actually good. This is not the same example when I was learning Rust, right? And I'll show you why. They're saying let R is up here. This is a lifetime of tick A. This is how you pronounce this. The line is, we say tick. So R is of lifetime tick A. X is of lifetime tick B. X goes out of scope with the bracket down here. A stays in scope the whole way. Therefore, the problem is the lifetime for A is larger than the lifetime for B. Therefore, you can't assign tick B to tick A. Right? Because tick A has to live. Tick A must live until all the way down here. Why? Because it's used right here. Right? This is the reason why this doesn't work. If you deleted this one line, this would compile. Tick A must live past this statement here because it's used right here. And the problem with tick B is that it doesn't live long enough to be used here. It goes out of scope. They're showing you another way to think about it here. Here's the thing. And we had this earlier, right? I want to say that it was one of you guys in the back corner that was asking this question. They said, when we're talking about it, how was the question asked? The question was like, when would I do something? And I couldn't think of a good answer until we went through this with like if. Well, let me think about it. I don't remember. I mean, I wish the classes were recorded because then I could definitely go back. I remember when we had the conversation. But what I was trying to show is something to the extent of this. Right down here, you can pretend like all of those brackets are there, even though they're not there. And here's what we have. We have let x equals 5, and let r equals a reference to x, and this down here. And in this case, we still have lifetimes, even though we don't have any explicit scoping. And this is what that looks like. That's when we did it. Okay, good. Oof. I was having a senior moment there. Sorry. Look at this. Check this out. Okay. This is what was going. Man, that was really bothering the shit out of me. I hate when that happens. Okay, look. This was the question that came up earlier in class, and now everyone's going to probably remember it. It was about shadowing. And we had something like this. I was doing, I want to say it was like let x equals 5, let x equals 10. And the question was, why would we ever want to allow shadowing like that? Right? Where you have the top x, the compiler is allowing you to override it with the bottom x. Why would I ever want that? Tab new, just so I don't have to deal with syntax highlighting when I'm writing. That doesn't work. The question was, why would I want to write that, right? Does anyone remember this?
Yeah.
Okay. This was the question, and I struggled to think about why you would need it, and I said I would not write it like that. The reason why you need it, though, is because I would write something like this, right? This is very common, because I could do something like this. That would be pretty normal, right? Because now I have a conditional. I have something inside of the conditional that's a different x. It's known by the same name of x. That's kind of normal, right? I have a different scope inside. But you would still say this x here is shadowing this x here, right? What they're showing you is, regardless of how you want to think about it, the lifetimes still exist. Here we have lifetimes that are explicit with brackets. Down here we don't have brackets, but the lifetimes still exist. I think these are somewhat related, right? This notion of having a lifetime without having an explicit scope. You can think about it the same way. It's the same way shadowing works, right? So here we have let x equals 5. Tick b is defined up here, and it's going to last all the way down until after you no longer need x. So how long do you need x for? Well, if you're going to say r is going to borrow a copy of x, and r is used down here, then x must live until at least r is done with it, right? And then it's showing you how long everything is going to live for. So r can go away right here, and tick b can go away right here. Both of these ticks can end right after this line. And that's what they're showing you. They end right there. Generic lifetimes and functions. Okay. So here's the problem with this. In the last implementation of longest, we were looking at an array, right? Or a vector. And we were saying a vector of any one type. And we were going to return the longest element in there that we owned. I don't think it was a reference. I think we actually said we were going to return one element, right? If we're going to return a reference, right, we need to know how long that reference will live for. You have to tell rest. So in this example here, we have a function called longest that takes an x and a y, and it returns a string. The question is a reference to a string, right? A string slice. How long does this string slice that it's returning need to live for? Does it live as long as the x, or does it live as long as the y?
So they both need to live the same amount. Otherwise we can't return.
Well, it's not necessarily true. What if, let's say, x can live shorter than the y, right? Like x has a smaller lifetime than the y. Then what we're returning can just live as long as the y. It doesn't have to live as long as the x, because y is going to live longer. Likewise, if x is the shorter one, and you want to return a lifetime that is shorter, that is also fine with the rest, so long as you're not referencing the lifetime that lives longer. Like, all of that kind of stuff has to be taken into account, and the compiler will help you out with all of it. It's just a pain in the butt. So here we have this function longest, and it takes an x and a y. And what they're showing you here is that you can say tick a. Now we have an a of tick a string and a y of tick a string, and we're returning a tick a string. So they're showing you that if you make one lifetime, you can make them all the same. But you don't have to do that. If you have more knowledge than that, you may not want to do it. Like, let me give you a case. I think I think everything I said was correct, but I don't think it was clear. Let me give you a case where that actually means something here. Josh, look at this one.
Okay.
Let's say I want to create something called find in, right? Have you aware of the terms needle and haystack in computer programming?
Not in your programming context.
You look for the needle in the haystack, right? So you typically use needle and haystack are the terms that we would use for that. So let's say that I want to say something called find in, and I say here needle, haystack, right? Now, what I'm going to be returning is going to be something from the haystack, right?
Yes.
Because that's what you're looking through. So I'm going to be returning a part of the haystack, right? So if I say right down here, let's say here, find in, I would say something like this. Yeah, let's just do this. Tick A, tick B, right? And you would want to do something like this. The needle would be of type tick A string. I think that's how it would look. Haystack would be of type tick B string. And then you're going to return something of type tick B string. There.
Gotcha.
Now, why does that make more sense? It makes more sense because now you can deallocate the needle the second you're done.
Yeah.
You don't need it. So in this one, I have explicit information, right? I don't have to live as long as the longest needle in haystack. I have to live as long as the haystack. You can drop the needle right away. Right after you find whatever you're looking for in the haystack, that thing, then you can drop the needle that you were given to look for.
Makes sense.
The search time. Okay. So what we're doing down here is actually I did that whole thing. See, the syntax is not right. This is what I'm saying. This is confusing even for me. So I actually was very close. None of these should be ampersand string. It should just be like this.
Is the ampersand at the beginning is
Right, exactly. That's exactly right. But I'm just saying, like, even that kind of syntax, I forget it because I don't write that code all the time.
yeah, it's,
I rely
it's
on my-
totally fair.
I rely on my editor to tell me, right?
Yeah.
And lifetime annotation syntax, there we go. So we have I32 as a reference. Here we have a reference to an I32 of lifetime tick A reference to a mutable I32 of lifetime of tick A. And these are just telling you how we say this or what we look at this as. Because this stuff here is confusing, right? Like, I really think that this is really the most confusing part about this, I think, is this stuff here. If you can wrap your head around where all these ampersands go and what these ticks mean, it makes a lot more sense. Because they get a lot more complex, too. Like, for instance, what do you do if you have a vector of references? Then you could have a reference that has a different lifetime than the thing that you're referring to. So the reference could be tick A, and then the lifetime of the type it's referencing could be tick B.
So I have nested lifetimes, basically.
Yeah, because you could say something like, this reference can't live longer than this lifetime, right? But I only need the type. I don't need the reference anymore, you know, or something like that. So I'm going to be returning something based on not the reference I get, but the type that I'm referring to. Here, FN longest tick A. Here we say tick A string, returning tick A. That's very easy. We've covered that one, I think, before on multiple occasions. The only thing there is that we're doing differently is we're doing the lifetimes, right? So this is just showing us this is the very same thing with just lifetimes. Let string 1 equals string from, the long string is long, and then string 2 equals XYZ, let result is longest, string 1 is string 2 is string, print the longest string is result. Okay, and I guess they're just showing you that the code works. No, they're showing you the code does not work. No. Yes.
It doesn't work when the print line isn't in the scope of the...
Ah, of course, obviously. Yes, result, it goes out here. Yeah.
It seems like an unrestricted sample. for the most part.
Attempting to use result after string 2 has gone out of scope. So with this definition of longest, the result has to live as long as both the inputs, x and y. And down here, they're showing you an example that hits on what we just talked about, right? The result does not live as long as x and y, right? So string 2 is going out of scope here. Therefore, result is not living as long as string 2. So that's where the error comes in. It says borrowed value does not live long enough, string 2. This is exactly what we just covered, right? The only difference is we use the word needle and haystack, and they're using, longest with, 2 different strings. But it's the same thing, right? Needle and haystack are both strings. Longest is taking 2 strings. They're showing you the same thing.
If that longest function only returned, sorry, could you scroll up a little bit more?
Yeah.
If it only returned string 1, or like lifetime of string 1, then that would compile though. But since it has the option of potentially returning like lifetime of string 2, it doesn't. Is that
Because
correct?
it's returning, when you declare it like this, right? When you declare it like they're declaring it here, fn longest, and they say here, x is of type tick A string, y is of type tick A string, and then it's returning something of type tick A string. What Russ is going to do internally is say, what does tick A equal in this context? It's going to be the most liberal interpretation possible. That means it's going to say, tick A needs to be long enough to hold x and long enough to hold y.
Yeah.
So it's going to be bigger than necessary.
Yeah.
And the problem with that is that it doesn't have to be long enough to hold y in this case. Because we can look at it and simply say, well, string 2 is shorter, it's not the longest. So if we know off the bat that string 2 is not going to be the longest, we can just fixate it to string 1.
Yeah.
And it would work. But, if it's going to have to fixate the lifetime to string 2 dies here, there's a problem. String 2 doesn't live long enough to do the time. Thinking in terms of lifetimes, good luck. God have mercy on your soul. This is, like I said, this is always the hardest part of us. It's the hardest part of everybody to get their heads around. And it represents just a small part of the language, too. Fn longest tick A, x is set to tick A string, and y is set to string slice, and it's going to return tick A string, right? So here's what we're solving that problem. We're essentially now saying that x has got an explicit type of tick A string, y is going to get, let me rephrase it. Remember when we started this, I said about implicit lifetimes? I said Rust has a notion of implicit lifetimes. It will infer lifetimes that are not written. Every reference has a lifetime, you just don't see it. Remember when I said that? What they're showing you here is you can give x an explicit lifetime in tick A. What's going to happen with y?
It'll be assigned its own implicit lifetime.
Exactly. Exactly. You specify lifetime parameter for A for the type parameter x and the return type, but not type parameter y. Because the lifetime of parameter y does not have any relationship with the lifetime of parameter x or the return value. So what will actually happen is y will get a new anonymous implicit lifetime that you won't be bothered with. Okay. And that's why that works. Because when I was speaking about this, I was saying we can give it 2 different explicit lifetimes for needle and haystack. That's one way to do it, but you can also just give one of them an explicit lifetime. And then we have this longest, and we have x and y, which are both string slices. And we're returning a string slice, and this is not working. And it's not working because you've specified the tick A for the return type. This implementation fails to compile, right? So the reason why this fails to compile is because the return type is of type tick A, but you have not said where tick A is.
Yeah.
So this is an important point. Everyone needs to get this point. This should have been the very beginning of the lesson. Lifetimes have to be on return types, right, if they're on input types. And if they're on return types, you have to say what input type they come from. So the purpose of a lifetime is to relate the input arguments with the output arguments. That's what the purpose of a lifetime is. The thing I'm going to return must live how long? If you're not returning anything and reference to anything, you don't ever have to bother with lifetimes. You only have to bother with lifetimes when you're returning references to stuff. So if you're going to return something of type tick A string, the compiler is going to say, hey, which one of these two is type tick A? That doesn't make sense. You're giving me a term, but you're not defining it. You need to define it. And this is what it says. Returns a reference to data owned by the current function. Right? It's not, you don't have the lifetime there. It cannot return reference to local variable result. That's a really horrible error message. That's a really bad error message. It should just say, you know, add tick A to one of the input types.
Well, the code just doesn't really make a lot of sense. One thing, I feel it's like you're returning a reference, right? So isn't that just going to instantly go out of scope when the function dies anyway?
Certainly, yes, yeah. Well, no, because what if you return a reference to something the function doesn't own? That's the whole purpose of this. In this case, it would die, because you're returning a reference to result, which you created in the function. But ideally, the only way it makes sense to return a reference is if you don't own it, right? So if you have a function, think about it, if you have a function and you're going to return a reference, you can't own, the function cannot own the thing it's returning a reference to.
Yeah, it has to be one of the input parameters.
Right, exactly, or something else in the program, right? Lifetime annotations and struct definitions. Here's where we go again. We have tick A, we have part, we're saying tick A string. They're just showing you here that you can do this with putting them right into the struct definitions. Lifetime Ellisons, these are kind of cool. Or elisions, I think. Lifetime elisions? Sounds better to me. Lifetime elisions. The reason why this works is because there are 3 different rules that there are in Rust that make it to where you don't have to write lifetimes when you think you would. Here we're saying S has one variable, which is a type of reference to string. So the return type is going to have what lifetime?
The same as the input.
Because there's only one thing, right? That's very simple. There are other examples too of this where you'll see this come into play, but there are 3 lifetime elision rules. These are all just shorthands of things you don't have to do. Lifetime annotations and method definitions. Let's cover this too. We have a method definition right here. So we're implementing for all, we're declaring a variable tick A for important excerpt, right? And we're saying there's a method called level, and it's going to return an I32, which is always 3. Oh, okay, never mind. So they're still going through the elision rules. There are 3 elision rules. The first elision rule is if you have one type, you know what it is. The second elision rule is if you have 2 different types, then they both get anonymous types. And I forget exactly what that is. The second rule is that if there's exactly one input parameter, that lifetime is assigned to all output lifetime parameters. Okay, so if you return multiple output parameters and you have one input parameter, it goes to all of them. Gotcha. And the third rule is if you have a reference to self, and that's all you take, then the thing you're returning must live as long as self. Right? So that's what they're going at with that. And this is for the purposes of making methods easy. Right? So here they're taking a self, and they're taking a string, and they're returning a string. So how long is this going to live for? That's the question. And the elision rules say that it's going to live as long as self lives. I want to say that's how it works. First we do anything called level and methods and groups. That's it, the first rule of each period, so lifetime. What's the third rule? The third rule is that if there are multiple input lifetime parameters, but one of them is self or mute self, because this is a method, the lifetime of self is assigned to all output parameters. Okay, good, I got that right. Oof. Okay, so I was just looking for where it said that. It said it way above it. So here, notice how we have two different references. We have a reference to self and a reference to the string, right? The output that you're returning, even though it's a string, it's going to be fixed not to the announcement, but to the self. It must live as long as the object, right? You can also change that explicitly if you want the other behavior. And the last thing that they have here is like the static lifetime stuff. Static is an interesting thing in Rust. It means that the lifetime must live as long as the program. So you can only declare static stuff in Rust, right, in specific places. You can't declare it everywhere, and you can't write to it. It can't be mutable. And this is a block of memory that gets initialized, and you can take references to it internally, but it doesn't ever get deallocated. It never gets cleaned up or destroyed. That's the definition of static in Rust.
Does const have an implicit static lifetime?
Yes, I think so. Yes. So, yes, I'm pretty sure that is true. So, the static string here, I have a static lifetime, is going to be tick static like this. And the advantage of that is you can use it anywhere in your code and you never have to use lifetime generics. Right? Because it's going to live forever. It's never going to get cleaned up. Let's briefly look at this. Okay, this is a pain in the ass. This is the one part that I didn't like. Generic type parameters, straight bounds, and lifetimes together. Here they're showing you a very complex example. Let's go through this and tell me what these are. Tick A. What is tick A, Josh?
Lifetime of A.
No, it's a lifetime. Good enough.
Okay.
Max, what is T?
That is a, what they call generic.
Type variable. That's right. Yeah, they're both generic. This is generic lifetime, this is generic type variable. Okay, tick A string is what?
It's a reference, or it's a string slice of lifetime.
That's exactly right. And T is what?
What is it called? Any like thing in there. It's type variable generic, so it can be really anything. It's sum.
Well, it's not sum,
No,
right?
anything option.
But yes, it can be anything, right? So it's a parameter to a function that can be anything, of any type, right? But let's come down here. Max, what is this? T display.
It is of any type that also conforms to display trait.
That's exactly right. So go back up and tell me what an is.
Alright, so now it knows that it has to be anything that conforms to display trait. It has to have a display trait in it.
That's right. Any type that implements a display trait. Exactly. So, and then we have right down here, we're printing out announcement of and, right? So, what is this going to do internally? How does this work?
It's going to be like, we're going to print out and whatever it is, because it has a display trait, it can be printed out. Right?
Exactly. That's the part I'm looking for. That's exactly right. Right, because you can only print out with these things, the double curly braces, look for the display trait. That's how they work. So to use the curly braces, the thing has to have the display trait implemented. Now, Josh, let's give you another level of it. If it doesn't have the display trait implemented, what compiler error will Rust give you?
They'll probably just tell you that it doesn't have display or debug implemented.
It'll tell you it doesn't have display implemented, and it'll tell you what? Perhaps you meant to use.
Perhaps, I don't know, sorry.
It'll say something like this. It'll say, this type does not have display implemented. Perhaps you meant to use curly bracket, colon, question mark curly bracket.
Fancy, the real fancy display out, so it could
Oh.
Right?
How does that work again? I've seen you use that multiple times instead of just the curly braces. I feel like I don't actually understand that.
Excellent. So the curly brackets, right, the curlies, mean that you're using display, which means you have to implement it. Which means you have to tell Rust, this is how I want that thing to be displayed to the user.
Okay.
It's specific to your application and your use case. It's for you. Debug is frequently you want to show everything,
Yeah.
right? Colon question mark inside of the curlies is the mnemonic is fancy. It's more complex because it's going to print everything, right? So you're adding complexity to your curly brackets with colon and question mark. And because you're adding that complexity to your curly brackets with the colon and question mark, you're going to get more verbose stuff,
Okay.
right? And that more verbose stuff is going to rely on the debug trait,
Okay.
right? So if a type implements the debug trait and not the display trait, and it gives you a warning, the display trait's not implemented for that type, Rust will come back and say, perhaps you meant to use colon question mark as the curlies, right? And that's probably one of the most common error messages. Because, you know, everyone wants the debug stuff, and very frequently they forget to use the colon and the question mark.
Yeah.
Okay, that's it. We're done.
Sweet.
I have one question.
Yes.
When did the HLUG group become the Uno card playing group?
Is that what they've been playing outside?
I remember when, even when we didn't have a class,
Yeah.
it was still more Linux, you know, it wasn't just a social club.
I don't have an answer to it, but quite frankly, I think it's great either way. Because there is less negativity. The only reason why we're having this class is Max. He's got to learn it. It's awesome that you're doing so badass, right? No, I mean, yeah. No. I'll give you shit later.
I've been wanting to learn Rust since it was done for a little bit in 2020.
I got a couple
At least
of
I know he got the best of you.
I got a couple of rustlings done without his help. Is that good for anything?
I'll give you a participation trophy. I know you're kind of nice. But I mean, I do think that like there's, you know, when someone comes up and say, hey, I want to learn Rust, and we have the effort to put it forward, it's nice to know that we don't drag down people who aren't interested in it. And to be quite frank, there's a lot of people who aren't interested in it, right?
Yeah.
Right, but the other group could be, you know, we could have a portion of the class where you do a lightning talk or do something, you know.
I fully agree, but I mean, the bottom line is that it takes someone like a Max to say, hey, I want to learn this. This is what I want to do. I want to learn how to be a computer programmer or something like that.
Yeah.
To get it kicked off. And if you don't have someone who wants to learn something, what you have is Uno players. You know,
Gotcha.
there's very few people who actually come forward and say, hey, I want to learn something.
I just remember when we were at cPanel originally, you know, we might have all been doing something, like everybody, you know, some people might have been trying to install Linux on their, whatever they dragged in and stuff like that. It was all Linux related. It wasn't just a social club. It wasn't just card playing.
It's hard to not chill when you have free sodas.
Yeah. I mean,
I missed that a little bit, that's all. The dynamic of that. Like even on a night when we didn't have a class, everybody, you know, people needed help with different things. One time I dragged an iMac in and we blew the dust out the back of it and we figured out, you know, it was a little glitch, but we got it.
one of the things that really hurt the group, I think, was Nikolai not coming as much. Like, the dynamic between me and him, I think, was very strong.
It was, but it just when I'm talking about even predates Nikolai.
Sure. You know, I'm not saying it's totally Nikolai, but I am saying that he added a lot to the group.
Yep.
Hey, if you guys want to help me clean out my computers, I'll just bring them. I have like 3 desktops that need to be cleaned.
Claim what they're saying.
I'm just saying, if you,
The
like,
dusting?
if you guys need to do something, I get to get my
man.
computers cleaned.
What's that?
I actually dropped the console off into one of the
And what are you gonna do while working on your computer? You gonna learn chess?
He's gonna play Uno.
Yeah.
This is the one I'm stuck on, I don't know how.
That's right, he's gonna play Uno.
You know what, actually, I had an idea for a project.
So I've got it again.
And so you know what the 3DS is? Nintendo 3DS.
One.
Okay, so how does each
Yeah, it's a
element
gaming
Handheld thing.
Yeah,
So-
it's ARM
So let me
architecture, actually,
read
so,
this.
you know, very
So back
cool.
loop is
but,
just the name of the
runs
function,
on
right?
Nintendo's web proprietary operating
Takes
system,
it back.
very big and